WMPG thrives with support from listeners and from Maine Solar Solutions. Maine Solar Solutions, helping empower homeowners and businesses with solar electric solutions for 10 years. Information at mainsolarsolutions.com.
You're listening to WMPG 90.9 Gorham, Portland, Southern Maine Community Radio from USM. Live from the Orion Cygnus arm of the Milky Way galaxy, this is Scientifically Speaking, and I forgot my intro.
Oh, that's good, Sarah.
Well, anyways, it's something about elegant curiosities, and I just had a brain fart. So we are a weekly half-hour program devoted to elegant curiosities, and I am one of your hosts, Sarah Chang, and joining me, as always, is Bernie Rhyme, DJ Star Watcher. How are you, Bernie?
Yeah, hi, Sarah. Very good. Thank you.
I'm struggling here. All right. Bernie is our professor of the astronomy lab here at USM and our local protector of the night skies. Reach out to us at WMPG Scientifically Speaking at gmail.com or on Twitter at WMPG SciSpeak. And you can head over to WMPG.org to find the last 5 weeks of archives of all of your favorite shows, including this one. Bernie, could you let our listeners know what is up in the night sky over this coming week?
Okay, certainly. So this will be Friday, November 25th. The Black Friday after Thanksgiving. We're actually in the studio, but it's still before Thanksgiving right now. So it's not quite live. So it will be a waxing crescent moon, which is the nicest phase. The new moon was on the 23rd. So you have the nice earth shine that you can see. So look for that in the waxing crescent moon if it's clear the next few days. So the first quarter moon will be on November 30th. And that's actually an important day because that's when Mars will be closest to the Earth in its 26th month. It actually is not going to be at opposition until December 8th when it's directly opposite and rises exactly at sunset. But it's going to be closer to the Earth. It's 50.6 million miles away, which by itself doesn't mean that much. It's about half the distance to the sun. It could get as close as about 35 million miles, which is a lot closer. So it'll be brighter and bigger. That happened in 2003. That was the closest approach in 60,000 years. So it'll still be good. However, it's going to be higher in the sky. So you have a trade-off. Obviously, it was bigger and brighter in 2003 than now, but it's like 70 degrees up in the sky in Taurus. So that means its light goes through less of the atmosphere. I looked at Mars through my telescope the other night, Monday night with my students, and you could see some of the features. I mean, you couldn't really make out the ice caps, but there were some features and some slight difference in color, and that you'll probably be able to see right through to the end of January. So definitely Mars is at its best. Jupiter just ended its retrograde motion on Thanksgiving, so it's back to its normal eastward motion. And then, of course, you can still see Saturn, but only maybe for another month. It's starting to set earlier and earlier. It probably sets by 9 or 10 at night, and pretty soon it'll be set by 8 o'clock, and then it's going to disappear in the west. And then actually later on in December, so a few more weeks, Mercury and Venus will show up again as evening planets. So all 7 planets will become evening planets, where just in June, all 7 planets were actually morning planets.
Oh.
So they all migrated to the evening. Of course, the 5 bright ones you can see, you would need a telescope for the other 2. But to know that they're all in the evening sky as of probably about roughly a week from now, start looking for them early in December. So later this week, you can see all the planets in the evening sky. Yep.
It's exciting. You know, I've never seen Neptune.
Oh, yeah, it's really nice. It's a bluish disk. It has a really neat color.
Can you see it at your guys' observatory?
Oh, yeah, of course. We have to.
Oh.
You need probably not even a 4-inch scope to see it.
Oh.
Yeah, and Uranus is kind of a nice greenish disk. It was actually being occulted by the eclipse moon that I saw back on November 8th.
Oh, no way.
But not right for us in Maine.
Yeah.
Because actually I would have set up my telescope if I remember I had written about it, but I wouldn't have seen it right where I was. But Uranus was at opposition and it was being occulted by a fully eclipsed moon.
Yeah.
On November 8th.
Yeah.
So.
Awesome.
And actually in Mars on December, we can talk about this before we do the next one, but December 7th, just before the opposition, the moon will actually occult or cover up Mars starting about 11 o'clock at night. And we're just on the southern boundary we'll be able to see that.
Oh.
I just wrote about that.
What does that look like?
I've seen other occultations. I've seen a daytime one of the moon covering up Venus. It's pretty impressive. It takes about 30 or 40 seconds for it to go out. It won't just flash out.
Yeah.
And then it's gone for about the width of the moon, so half an hour to 40 minutes. And then it shows up on the other side. You really get a sense of the moon's motion. Mm-hmm. The planet disappears, reappears. It's a pretty neat event. You would need a telescope, because if you're just looking at it, you could see it, but you don't appreciate the different things. You can see it without one. But with the scope, you can get all the details. Mars at its best, the moon occulting it, all these neat things happening December 7th and 8th.
That's awesome.
Yeah.
Yeah, so that's like 2 weeks away.
Yeah, right.
And I do have to give a shout out to Jessica, our production manager, who said because of us, she got up early to go see
Oh, good.
the lunar eclipse.
Yeah, I made a few people get up early too.
Yeah, and so I love that. I love when people tell us that they were, I don't know if they do it because of us or for
Probably the
us
event,
or
but at
what.
least they would have forgotten about it or not
Yeah.
have been urged on to do it.
Yeah.
And it's always worth it. I mean, the weather. Actually, I talked to some other people, and they said the weather wasn't that great further up north in Maine, but it was
Oh.
perfect for us and most people
Yeah,
in our
it was
listening
not
area.
too bad.
It was
here.
perfect. Couple clouds after the eclipse started, but they didn't really bother anything. Yeah, it was worth it.
Yeah, I mean that was such a great time too because then you got to see the moon set, and then the very next day moonrise was full. So
Yeah, well,
yeah,
it
I missed
was,
both though.
You missed them both? Yeah, and then, of course, the next day it was still looked almost full, and it came out maybe 45 minutes later, but of course it wasn't in our shadow anymore. But yeah, it was kind of neat to see all that and picture the sunrise and then all the sunrises at the same time on the moon, and you get to see one sunrise yourself.
Yep.
I've never seen one at sunrise before. Yeah.
Yeah.
You really see how you get a sense of
Yeah.
how you line up. I mean, any eclipse is created by a perfect alignment when you have to be in it. But when you get the actual sunrise and moon set, then you can picture that alignment a lot better. One person said that I talked to at one of my clubs, he actually said he felt like he was in space at the time. And and then I told him about he never saw a solar eclipse. But when you see a total solar eclipse, you feel even more like you're in space watching the whole thing from a whole different perspective. But he got that sense from the lunar eclipse, which is good because I was just recently able to do that, picturing the shadows, the three-dimensional nature, being in space, watching the whole thing at once, getting a sense of our entire atmosphere at once, which is much more clear in a solar eclipse. But it's there in a lunar eclipse. It's more subtle, but you have to know it.
Right.
And I'm glad this person who was just a friend, that he was able to sense that just by watching this lunar eclipse.
Yeah.
So be aware of that too when you watch other eclipses.
Yeah.
Yeah.
And think about how small you are in this world.
Yeah, well, right, of course. But the fact that you can see and understand all this so far beyond, yeah, of course, the whole Earth is not even a dust mote, but you can understand all this stuff. That's the amazing thing, I think.
Yeah.
Yeah.
Awesome. Well, thank you, Bernie.
Sure.
And if you couldn't take notes fast enough, you can also check out the monthly What's Up column in the Portland Press Herald. All right. So for today's show, today's episode of Scientifically Speaking, we are celebrating as started by Seth and Edward, right?
Yeah.
This tradition of Black Hole Friday. So we're not advocating for you guys to go out there and spend money, but rather let's talk about black holes. And so we have some updates on black holes, some of the new discoveries that have happened that have, allowed just a little bit more about these very strange objects in space. And Bernie, why don't you start us off with giving us a little primer on black holes?
Yeah. Okay. Well, I'll just say a few basic things about them, and then I'll do what I'll explain. Like, there's 5 different levels. There's a astrophysicist that works with Neil deGrasse Tyson in New York City named Jen Levin. So, and other people do this on other topics like quantum computers or something like that. At different levels. So they'll bring in like an elementary school person and a school person, a college student, and then a professor that teaches with her. So you get a sense of, different levels of how intricate and how you can explain black holes and so on. So before I do that though, I'll basically start with saying that you could essentially turn anything into a black hole because it's just really a summary of space and time. So, this, of course, was predicted by Einstein back in 1915, and we actually found one in 2015. We'll talk about a little bit about the chirp, the image we got of the gravitational waves generated. And then we got a picture of one in 2019, and we've gotten some pictures of them. So they've given out some Nobel Prizes, too, last year on black holes. So now it's very real, but, of course, they still have a lot of mysteries. So just to give you a size and a comparison, also, so if you could shrink the Earth down enough to the size of a marble, about an inch across, it would be dense enough to be a black hole. So that's 8,000 miles of what you think is solid. Of course, the Earth isn't solid because every atom is mostly empty space. And then if you shrink the sun down to about 2 miles, it would be dense enough to be a black hole. but it's not massive enough to generate a black hole when it dies. So you have all different types of black holes. You have stellar mass black holes, probably around 4 or 5 solar masses. Of course, you get the neutron star and then the black hole version. And then you have the supermassive black holes at the center of galaxies. All the galaxies have one. The smaller ones, like even the satellite galaxies of our own, they have smaller black holes at their center, maybe only 10 or 20 solar masses. And some really small galaxies would not have them. And then you have potentially the primordial or the mini black holes, but that hasn't really been proven. So there's like 3 different types of black holes. All right, so the way she started, there was an elementary school person came in, and this was just set up probably in New York, probably at the Science Museum where she is. So basically, were just the usual things there, like, not even light can escape from the black hole. And she explained, like I just did, that the sun wouldn't be heavy enough to turn into a black hole. But the thing here, like the black hole actually changes the shape of the space around it. I mean, you get this gravity well. I mean, any object with mass will do this. I mean, the Earth has a gravity well, and the moon orbits in it. The sun has one in it. The 8 planets orbit around it. So the black hole has an even more intense gravity well. And then she just said something about, like, the person was sitting in a chair, and it's almost like moving that chair without actually, touching the chair, just the gravity well around it.
Yeah.
So that's kind of how, and we measure the mass of black holes by how the stars move around it. So that's how we can figure out the mass. All right, so then we had a high school student, and actually she was kind of interesting. She actually was playing some electric guitar, and she made some good connections there. So if the black hole is massive enough, it could tear apart neighboring stars. And so what she said there is that, like the electric guitar, if it's not plugged in, you wouldn't hear it. So that would be like, so the black hole would be like the mallets on a drum. So the sounds would be what you're hearing, so the energy spread through space-time.
Yeah.
And that's how we picked up the first signal of it back in 2015. That's what you were kind of hearing. Otherwise, of course, you wouldn't hear it. I mean, you have to have a medium to transmit that. And then, well, I don't know if we'll talk a little bit about LIGO. So but the neat thing here is you can kind of reconstruct what happened and the mass of the black holes and everything just by seeing those waves. So the one that we first saw like 7 years ago now, that was 2 supermassive black holes, each one about 40 solar masses. And when they merged, it ended up with one about 75, and 5 solar masses of energy went into moving the space-time fabric, which we picked up 1.3 billion years after it happened.
So when you say it's solar mass of energy,
yeah,
you mean that's like if you were saying what is one solar mass energy is the amount of energy that the sun would...
Well, solar mass is the mass. I mean, energy equals mass based on E equals mc squared.
Yeah.
But just as a reference, we are one solar mass. If it's heavier or less, we use that. So so that the 2 black holes, they were each about 40 solar masses.
Yeah.
Again, we could tell that from the stars around them. So we can reconstruct that, and black holes have a lot to do with information, some other neat things too. And we have some other detectors now. There's one called Virgo in Italy, and one called Libra, and there's another one in Germany is 600 something, meaning it's 600 meters long.
I didn't want to do another constellation.
Oh, that's right, Virgo. Yeah, that's right, the constellations. Yeah. All right, so then we had a person that is actually studying some physics and environmental science in college. So then they talk about the event horizon, and so of course, as the core is heavy enough, it'll just keep collapsing, and it'll leave behind a record. And then actually, Jana even got into the fact that actually black holes could be almost seen like a fundamental particle or like an electron. And of course, there's a singularity at the center, but you don't really know what happens as you kind of go into it. I mean, she actually related one to being like potentially a giant battery or something. She has some interesting... Of course, you can't test any of this because you can't make one in a lab or something. So you have to test it all with math. So there were some new things about that. And then they had the PhD person who actually teaches at City University in New York. And he was talking about the Hawking radiation, which is fairly new, that actually it shows that black holes eventually do evaporate. I mean, they have like black body radiation, they evaporate. It would take a long time for the large ones. Of course, the smaller ones would take less time. They're actually hotter. The bigger ones, like the one at the center of M87, they would evaporate in like trillions of years. So another way then to look at black holes is they're not really just life takers because, material just doesn't fall in. They're also life givers in a way because they recreate the conditions then when new stars can form when they kind of blow up. Almost like a supernova recycles the elements back into the galaxy. But the black holes do it through gravitational waves and not electromagnetic. So then you have the Hawking radiation. There's all the mysteries about, of course, quantum mechanics and when you get inside of one, how quantum gravity might work, and get really involved in theoretical as to what is going on inside of them. But it's neat because there's always new things they can learn about it mathematically. And even, of course, you probably heard of if someone goes in, they would be spaghettified.
Yep.
They would kind of stay on the event horizon if you have an outside observer. Okay, like all the information and the light kind of piles up there, and then that would eventually disappear. They wouldn't stay there forever.
Yeah.
But you wouldn't actually never know what happens because if you try to measure it, you need a wavelength short enough to measure that, and you would fry the person or the electron or the photon that went in. So from the point of view of someone that went in, you really don't know, and you have no way of measuring because that's true of the way you would measure and see anything. You need the wavelength so just going in there, and of course, and the reason you would get spaghettified is because the gravitational energy of the black hole at the event horizon would just override the electromagnetic energy that's keeping your molecules together. Normally, gravity is extremely weak, but if you concentrate it, I look at black holes as like pure gravity. If you concentrate it that way, it would override your other much weaker forces, and that's the reason that would happen. And the other neat thing is you're reversing space and time. So when you go in, normally you move through time, but space is your option. Well, at the black hole, you're moving through space, and time is actually reversed. So if you think of that complete reversal, like an hourglass and then going in, then you can get some really neat math and get a better idea what a black hole is.
Yeah. Going back to your spaghettification.
Yeah.
So just to clarify for listeners, spaghettification is sometimes also referred to as the noodle effect. I've actually never heard it that way, but it's the vertical stretching and horizontal compression of objects into long shapes, kind of like spaghetti, in a very strong and non-homogeneous gravitational field. So that's that's a good example is the hourglass, like the time. What are those called?
Well,
time turners.
Yeah.
Yeah.
Well, when time and space get reversed, that's a neater way of looking at it. Just having a steep gravity well, you actually reverse them.
Yep. And actually, so just going into kind of some recent news, in October of this year, scientists found that black holes can burp up shredded stars. And so it's kind of like what you're talking about. They do kind of emit some, stuff. This was a little bit different. It didn't necessarily make the conclusion that it was useful stuff. But basically, for the first time, astronomers have seen like black holes kind of spewing stellar remains years after consuming a star. The way that the analogy that they used was that, like, yes, it's kind of like burping after a meal, but it also is kind of like describing a black hole as a very messy eater. So it's like, you know how like the Cookie Monster in Sesame Street, it's like technically eating the cookie, but it's really just like crunching it up and all the cookie stuff is like being ejected. That's kind of like how they're describing it. So black holes are ejecting material that travels at about half the speed of light. But they're not sure why the outflow is delayed by several years. And so basically there was a team at the Center for Astrophysics in like Harvard and Smithsonian CFA. And so they had noticed an unusual outburst while revisiting tidal disruption events, or TDEs. And that's when encroaching stars are, like Bernie was saying, kind of stretched and compressed or spaghettified, essentially, by black holes. And this is kind of like over the last several years. And they basically got radio data from the Very Large Array in New Mexico that showed that a black hole had mysteriously reanimated in June of 2021. And so they had been studying like TDEs with radio telescopes for more than a decade. Sometimes they'll find like a shine in radio waves, but when like a star is being first consumed, but rarely at the end, like later when there's no consumption being happening. And so anyways, I think what they found is that this emission, known as an outflow, normally develops quickly after a TDE occurs, when something is being consumed, and not necessarily years later. And so they basically just describe it as if a black hole has started abruptly burping out a bunch of material from the start at 8 years ago.
Mm-hmm. Yeah.
So, interesting stuff.
So that's different than the normal. I mean,
little
some of
bit
the
different,
active
yep.
black holes are constantly putting out a lot
Right.
jets at 99% the speed of light. The one like 180. It's called an active galactic nuclei. And there may be only 1% of that.
Yep.
But the neat thing about our own galaxy, the massive black hole there used to be active, but it hasn't been for a long time.
Okay.
So,
Yeah. Cool. Neat. Do we want to talk, because you were talking about not clicks. What are those called? Clips.
Oh, the chirp?
Chirps.
When we first saw one with LIGO.
Yeah.
I think it was about 2015.
All right. So we've got
Black hole
a couple.
mergers.
Yeah,
Yep.
we've got a couple of like sound things that we want to share with listeners. And since you had mentioned the chirps,
Yep.
so we wanted to show what that sounds like to you, and this is really short. And then we'll also, so NASA's Chandra X-ray scope has, like, there's some data from that NASA's, they're called like sound astronomers, I guess is what their official title, but they have sonified some of the like waves and the data from that specific telescope. So here is what a chirp sounds like, and this is essentially like that little blip that, like, as two black holes are merging, right? And there's just it's like the kaboom.
Yeah.
Right?
Yeah.
All right, let's see if we can play this. Did you hear that?
Yep. So it takes a long time for them to get close, and then only about less than 1 second.
Yep.
And then you have like 5 solar masses of energy that goes into stretching and compressing space-time.
Yep.
Because the black hole after that is only about 75 solar masses instead
Yep.
of 80. And it levels itself off very nicely.
Yeah,
because black hole is generally perfectly round unless it's spinning. It's really very simple. It only has mass, charge, and spin. That's really all it has. So it's pretty easy theoretically to figure out what it is.
Yep.
Yeah.
So that's just like a sonified version of the waves coming from the black hole mergers. And there's several samples, but there's kind of the bassy one, and then they pitched it up for the second one so you could like listen to it differently.
Yeah.
All right, so on to kind of further black hole sonification. So in 2003, the black hole at the center of the Perseus galaxy cluster has actually been associated with sound. And that's just because astronomers had discovered that there were pressure waves being sent out by the black hole, which caused ripples in the cluster's hot gas, which could then, that it was the medium for which you could listen to this sound. And this was, we had an episode a long time ago about sound in outer space. But this particular sound coming from the Perseus galaxy was a sound that we could not hear about 57 octaves below middle C. Do you remember that?
Yeah, it's
You
pretty
remember
low.
we talked about that.
Yeah.
And so anyways, kind of recently this year in May, NASA's kind of sound astronomer team had sonified a couple of some data. So basically data turned into sound waves from NASA's Chandra X-ray Observatory. And again, like Bernie was mentioning, we kind of don't expect there to be sound because space is a vacuum. Essentially, there's no medium for sound, but in kind of clusters and there's a lot of gas, and that allows, that's a medium for sound waves to travel.
Yep.
And so essentially, the astronomers basically identified these data points. They extract them, made them audible, and they can resynthesize them into the range of human hearing they essentially have to scale it up by 57 or 58
quite a bit.
octaves above their true pitch. And yeah, it's so another way to put this is that they are being heard 144 quadrillion and 288 quadrillion times higher than their original frequency. And a quadrillion is a one with
15.
five triplets of zeros.
Yeah, 15.
Yes,
5
yes.
times 3.
Yep.
Yeah, 15.
Yep.
Mm-hmm.
All right. So what we're gonna do is I've got two sound clips here. This is from NASA, and they call it. They've like remixed essentially these sonifications. So this is the one from the Perseus galaxy that we were talking about. Can you hear that? Kind of.
Yeah, we're watching a beam sweep across on the waves too, so
Yep.
we can see the sound too that you can just hear. Yeah.
Yeah, and I mean, there's some like I think there's some artistic freedom
License,
here.
yeah.
Yeah, but I think that one is pretty good at. I mean, it seems
Once
like
they
it
raise
mimics
it by the
but
57
yeah,
octaves
it seems
and
like it makes
everything,
it.
yeah.
Yep. And so the other one that I wanted to share is Messier 87, which it
The
was
first one to
for
get the image.
first
Yeah.
one from the Event Horizon Telescope, and NASA also did sonify data from M87. But not from the Event Horizon Telescope, but data from kind of a lot of other telescopes. And this one, I think, has a little bit more artistic freedom here, but it you can still kind of hear it. So let's play this.
Yeah, that one actually shoots 5,000 light years into space.
Wow.
And it's pointed right at us, but it's 50 million light years away. So we're okay. Otherwise, we would be fried by that right now. Totally fried. 99% the speed of light, 5,000 light years long. We'd be fried.
So that sound wave was actually it maps radio waves to the lowest tones, optical data to medium tones, and X-rays detected by Chandra to the highest tones. And obviously, I do think there was probably some, I don't know, nice sounding music in
Yeah.
there, but you could kind of hear that. And it's kind of cool. There's obviously a lot of different ways you can sonify this data, but those are kind of a couple of examples that we wanted to share. All right. So, man, we're down to like the last minute here.
Oh.
Yeah.
Mm-hmm.
What is like one
Yeah.
last thing you want your listeners
Well,
to take
yeah,
away
so one
from
of the
here?
neat new things, and I was listening to all kinds of lectures by Leonard Susskind. He's one of the top physicists in the world. I'm sure he's written some books too. So his now is some of the new theories involve that the event horizon of the black hole, like that point of no return we were talking about, that may actually encode all the information, because there's a big thing in quantum mechanics about losing information in a black hole. Like if you burn up a piece of paper and you only have the ash left, theoretically you can reconstruct it all from that. Of course, some would be in the air, it'd be kind of tough. Well, the same with the black hole. If you never lose that information, it has to be there. So everything might be encoded on a two-dimensional event horizon and projected out as 3 dimensions. So basically that leads to the holographic principle. So the whole universe could kind of be a hologram, and we could actually be in a black hole because we have an event horizon, which is as far as we can see, which is about 50 billion light years out, just based on the speed of light. That's as far as we can see. So we could be that. And then if everything gets projected out this way, I mean, there's so much information at the Planck length. You could take everything down to 10 to the minus 35 meters. You'd have enough information space on that event horizon to project everything out from there.
Yeah, that's
So
awesome.
some of the newest theories that
Yeah.
he has come up with.
It's exciting.
Yeah.
Well,
Yep.
that's Black Hole Friday for you guys. Happy Black Hole Friday. And hopefully you had also a wonderful holiday if you celebrate. And with that, I've got one joke for you.
Okay.
What did the black hole say after it swallowed an asteroid?
I don't know. What did it say?
It was good, but I wish it had been a little meteor.
Meteor.
Yeah.
No, a little meteor. That's good. Not a meteorite, but a little meteor. That's
All
good.
right.
Yes.
You've been listening to Scientifically Speaking here on WMPG with myself and Bernie. Stay tuned for What's in My Mind by the fabulous Emma. And from your favorite nerds, enjoy, the weekend. Hopefully you've stuffed yourselves full and you're exercising it off. All right.